Hello, everyone, and welcome to another Quanser live webinar. This is a webinar of Accelerating Through the Apex, teaching with Quanser's self-driving car studio. My name is John Pineros. Together with my colleague Gemma Wang, I'll be your host and moderator this morning. Today's webinar will be presented by R&D engineer Dr. Mitchell Rushton. He's involved in developing research examples, teaching content, and extending Quanser's application libraries. Dr. Rushton holds a PhD in mechatronics and engineering and a certificate in university teaching from the University of Waterloo, where he has taught as a sessional instructor. His research interests include vibration control and cable-driven parallel robots with applications to rehabilitation and automated warehousing.
So as my colleague John has started off with, today we're going to be talking about teaching with Quanser's self-driving car studio and how Quanser's self-driving car studio can be used in particular for teaching. And the motivations behind this webinar are twofold. The first off being to we've gotten feedback that there's a growing need in academia as well, with changes in industry for more teaching focused on the skills students need for autonomous vehicle technology and autonomous robots in general, but in particular self-driving cars, in a way that's accessible to undergraduate students. And as well, one of the ways, well, the best way, certainly Quanser believes often for many things is hands-on learning experiences are something that really provides insight in ways that simple textbook or other things can't provide. And so promoting the idea of a hands-on learning experiences is a way for students to develop these skills to make them more competitive as they try to eventually launch their careers in the industry. So the agenda, nothing too fancy here, but starting with, just want to give you some background on what SDCS is and what the Q car is in case you're not familiar. And then go over some of the new content we've been developing, specifically with education in mind, making use of our existing QCard platform, and then make some final statements before going into our Q&A. So as a background, Quanser's self-driving car studio, it's a product or a collection of products, perhaps first developed and launched in 2020. You can see it consists of the Q car itself, which is the primary, I guess, the centerpiece of it. But in addition, you see, really, we provide a complete, like a design studio. It's a mini city, really. It comes with the road maps. You get 10th scale traffic lights and road signs. You can have multiple vehicles driving around in this 1/10 city, which is much easier to fit in your lab than an actual city. Hence the benefit there. Aside from being 1/10 the size of a regular car, it's pretty much the same as what you would find in an actual self-driving car. It's got all the sensors. It's got 360-degree cameras. It's got, as well as the depth camera, LiDAR, accelerometers, encoders, Ackerman steering, differential, all these things. So a good way of replicating the experience, and certainly the skills you acquire learning on this platform is directly transferable to an actual automotive application. Now, when we launched this originally and up until this point, really, the focus has entirely been on research. And in fact, initially, this was called the self-driving car research studio. We've since taken out the research because we want to emphasize it's not just for research anymore. It's also can serve the dual purpose of education, especially as the fields behind self-driving cars become more solidified and branching out just from academic research into actual industry, and then trickling down to undergraduate course offerings simultaneously. In addition to the physical setup, a part of what we come with is Quanser Interactive Labs, short name Q Labs. And this is our digital twin, not just for Q car, for most of Quanser's products, but it's our digital simulation environment that mirrors the physical device. And the idea here, this is particularly beneficial for a teaching environment, is that it gives students the ability to develop and test their code on their own time outside of the lab. And so they can develop their code, go through the time-consuming debugging parts, getting their code up and running at home. So they don't have to waste precious time with the actual device. Typically, in a course of 100 students, it's not feasible to have 100 cue cards, right? Obviously, it's cost prohibitive, but maybe you'll have 3 or 4, and if students can do the bulk of their work at home, they can then transfer their results from the simulated environment to the actual physical car and be able to have really make it much more accessible to larger class sizes without a insurmountable financial burden preventing those students from getting that experience. And the other aspect as well is it really encourages continuous learning and experimentation for students, especially students that are eager and want to learn and do more. If you're only giving them a few hours a week to actually touch the hardware, no matter how much motivation they have, they're really limited in what they can do. But giving them 24-hour access to this platform where they can play with it, they can experiment, they can try out their ideas. It really is for the student who has the motivation, you can do quite a lot. And it's fun. I mean, so that's the other thing. Yes. So in particular for a teaching situation, QLabs really is quite a valuable pairing there. So that's the summary of basically of what SDCS is and has been to this point. But again, everything we've done previously was really tailored toward a research audience. And so just recently we started developing as well and releasing it slowly, more content to support some of these more education-oriented endeavors. And so for now, some of the 3 main things we've developed and we want to release and talk about now is this main body of content that you see. So there's 3 main categories. We have the concept reviews, skills activities, and as well we've updated a set of additional Python libraries to make all of it easier to get in touch with. So looking at the software support that QCars had up until this point, we've supported both Simulink, ROS, and ROS nodes in both Python and C++. Most of Quanser's work is, if you're familiar with, has been focused heavily on Simulink and MATLAB using Quark, which is our real-time software library that sits within, well, is embedded in Simulink. And so actually using Python, purely Python, for more complicated material is actually a relatively new thing for Quanser. And so we've been working hard actually to make, to be able to provide a greater level of support, not just bare level hardware support, but actually more useful things as well, going beyond just interacting with the hardware, but how to do some of the more complex tasks that you might want to do to serve an actual application. And so why Python for teaching, or why Python at all? Really, I mean, a large part of it's responding to the demand that we've gotten in recent years. Actually, I'll shoot ahead to this. If you look at the popularity of Python over time, really in the last, since 2018, the popularity of Python has exploded quite significantly. It seems to be continuing on that trend. It was stagnant fairly for the last few decades, but since then it's taken off, and it's now ranked by multiple metrics that try to assess these things as the most popular programming language by far. And as well, this is from a recent IEEE Spectrum article looking at skills that software engineers need to know based on perceptions of 1,600 engineers that were surveyed. And Python takes the top spot by a large margin. But if you look at the languages and technologies that are on there, most of them are for web development. And so if you filter out ones that are specifically for web, which is not really relevant for robotics or self-driving cars or anything like that, it makes Python's dominance that much more clear. And to quote, I typically expect them, if you're a software engineer and you don't know Python, you know, time to start. And so because of that, really this trend which has happened in the last few years is something that both customers have been asking for, but as well something that we feel like we need to respond to. And so we've taken that and responded to it. But otherwise, aside from that, the industry pressure it really is an ideal platform for teaching for a few reasons. It's free, which is obviously nice, but it's also cross-platform as opposed to thinking like something like content within ROS, um, which is more difficult, particularly on Windows, which many students like, or Mac. Um, and as well, it gives you a seamless transition between virtual and our physical environments. And the other thing is that it's very simple and pain-free to set up. And this might not sound like a lot, but if you've ever tried to use ROS, particularly in a teaching setting, uh, it often devolves into quite the nightmare. Many students struggling, spending significant amounts of times just to get their development environment set up, uh, which again, that's time that's wasted from the actual teaching objectives of your course, and it really takes away from the main picture of what it is you're trying to convey. If it's something like controls or perception, and it really gets in the way of what you can achieve during the limited time frame of course. And so we want to get rid of that burden and really try to make it as simple and easy to get going, so you can maximize the time you spent on actually useful things. Um, And so because of that, we've started developing a new set of Python application libraries. And the idea here is to extend beyond what just the low-level hardware and the loot libraries that we already provide from Quark, to take it beyond just interfacing with hardware, but also to try and minimize the friction between what you want to do with our hardware and our hardware itself. Try to make it as easy and pain-free to get up and running and to test whatever idea, whatever concept or skill you're trying to get students to learn, or experience you're trying to create for them, minimize taking the barriers away to actually do that. Um, this is something working on currently quite actively, actually, really just for the last 6 months, but continuing to keep working on it actively for all products, but in particular for SDCS, which has been the main driving force here. Um, just looking at the format of it, we have two primary packages that we're putting out, PAL and HAL, PAL being the Python application libraries and HAL is more higher level application libraries. The distinction there is made because sometimes, depending on the course content you're teaching, you don't necessarily want to give students solutions to things that they're going to be performing in the lab. With SDCS, you get both, because SDCS is kind of special, but we have specific modules for each product, as well as specific modules devoted to things that are more product agnostic, generic things. Like, for example, if you look at pal.utilities, we have simplified classes for dealing with gamepads. We have a scope dealing with cameras in general, or LiDARs in general, not necessarily any particular product's LiDAR. But then pal.products, you have uh, the QCAR, which will have specific implementations for it. So if you look at the QCAR, for example, we have classes for each of the different hardware systems in the QCAR. For example, QCAR cameras. And so not only does this make the hardware interfacing very straightforward, it also deals with the low-level tasks, which are unnecessary in most cases. Things like calibrations of the cameras and having the calibration matrices in line properly and all these other low-level things you don't necessarily care about if all you want to teach is about object detection. Same story with all the other devices. We have a QCard GPS, which simulates the functionality of a GPS, so you can get a position estimate within the room of where the car is, and other features like this. As far as the higher level functionality is concerned, we have a few things at the moment. So again, depending on what you want to do, you don't necessarily want to reinvent the entire set of wheels every time. And so we give you our implementations for a number of things, basic tasks which you need just to get up and going. We have a QCar which gives you a state estimate of the car. It's our implementation of a state estimator, which we find to work pretty well, and so we give it to you. So if you want a state estimate of the car, you just create an instance of this class and you're done. Same thing, we give you a drive controller. If you want to drive around the city, you can use our drive controller and it works pretty well. We have geometry, which shows you the transformation matrices to all of the different frames of reference on the car, be it the LiDAR, the cameras, the front and rear axle, all these different things. And so this saves you a lot of time dealing with that. And as well, we have a roadmap class, which you can use for creating paths between any 2 points. It's a trajectory generation class, basically. So you can create a path throughout our cityscape. So these are some of the things. Again, it's constantly it's very dynamic at the moment. We're constantly adding new things. Every time we come up with something new, we add it to the libraries. So it's going to continue to expand over the next year for sure. And so using these Python libraries, we then have gone ahead and created a number of skills activities. And this is the big thing, and really a distinction from other course offerings we've had in the past. They're not labs in the typical sense, and they're not intended to be. They're seen as more of an interactive, hands-on experience to really get a tangible grasp on how how different aspects of self-driving work and the effects of being able to compare and play with different parameters and things like this. That being said, it's designed to be completely flexible to be whatever you want it to be. And one of those distinctions is that we give you the solutions to whatever activity is being performed with the aim of being performed in that activity. We give you the solutions. So on the right, for example, you can see this is from the state estimation one. And so there's sections commented out, which are our suggested solutions. And they're commented out by default, but you're free to uncomment them if you like and use them, or you can have them removed completely before you give them to students if you don't want students to see them. But not everyone, I mean, the intention, depending on the year of the students and your goals, you may or may not want them there. But we give them to you and you have that choice. Accompanied with each of the activities, we have a detailed lab guide, which we can use to guide students through performing the steps should they want to either implement it themselves or just experiment with the different possible algorithms. Supporting each of our skills activities, we also have a large number of skills activities, I think 16 at the moment, devoted to relevant topics and technical content that they need to understand. And this can be intended as just to support a reference to reinforce things they're learning throughout the course, or as well just background readings. So we cover many things like, well, you can see here, kinematic modeling of a car or occupancy grid mapping. We also have things on controls, lateral control, PID, things like this. And so these guides are very helpful for support. And so the initial set of, initially we're releasing 5 distinct skills activities. And again, in distinction between the labs, they're not all necessarily of the same weight. Some of them are quite actually involved. The environment interpretation lab, for example, as well the state estimation, they can be quite involved, depending on how deep you want to go with them. Other ones less so. And so really what we plan to achieve with this set is go over some of the foundations of self-driving technology, and starting from the bare basics, and then by the end of the set, you've built really a form of a full self-driving stack. And each lab can be, well, each activity, really they're designed to be able to be performed independently. So the code is set up so that you only need to modify the part that's relevant to that specific task. That being said, they are also designed in a way so that if you want to have a progression, they are set up to do that. And so, for example, vehicle environment interpretation requires vehicle control, which requires state estimation, which requires being able to interface with the sensors, and so on. And so it depends on how you want to do. It does create a nice progression where you can see over the course of a term, starting from nothing and then really feeling the accomplishment at the end when you've created a complex task, to be able to perform a complex task autonomously. Uh, so looking at the first one, into image interpretation, the focus on this here is understanding how cameras work, basically, and how we interface with them, the type of data that they spit out, and some of the inherent hardware issues that we experience with them. One of which you can see on the left, the top left, the image there. There's some significant barrel distortion on the image. And this is what a raw image looks like when you first read from a sensor, a camera sensor. And so always we need to perform some type of calibration on it so we can get a more useful reading. And typically this is done with a something like a checkerboard pattern, which you can see. And so we go through the process of explaining and performing camera calibration. And then once we have a calibrated image, you can perform image processing tasks like line detection. And so you can see the resulting on the right, the red lines being straight lines detected within our matrix. And for all the activities, they're both, again, performed identically within either the virtual or the physical. So we have our virtual checkerboard there, as you can see. The second lab is focused on sensors and sensor interfacing, how we read from sensors and how do we interpret the signals that they're actually sending us. And so in addition to reading from the DAC and processing what it spits out, we look at sensor noise and noise models and how we can estimate the parameters for a noisy signal. So for example, here you can see some gyroscope data, and then we go through plotting the histogram, estimating the mean and variance, and then we can fit it to a nice Gaussian for each of our sensors, which we can then use for our next lab, which is our next activity on state estimation. And so in this activity, the focus is on estimating the state of the car, where it is in space. So the position in 2D space, as well as the heading angle. And so we look at a few different algorithms here to do it of increasing complexity. The first, which in the graph you can see is the red, is just dead reckoning. So we use a kinematic bicycle model, but if we just look at the encoder and integrate, eventually it accumulates errors with time. Because wheels slip and other things like this, it's not a perfect model. And so we need to use more sensor information to correct the deviations and errors. And so we created the next step. We have an extended Kalman filter that's just based on the GPS. And then we have a more complicated cascaded EKF KF estimator, which is fusing together gyroscope data and GPS and the encoder and all these things. So you get to look at what's the effect of adding more information and things like this, and how the type of role that sensor fusion can play, as well as the specific technical details of how to actually do it. And if you want to go through the effort of implementing an extended Kalman filter, you can do that. But it's also can be done topically if you want to just look at what's the actual result of what you get from using these different types of sensors, and the performance of having more information. Oh yeah, the scope on the bottom there, that's showing you for the more complicated filter, we also estimate the gyroscope bias, which is another thing we talk about, some of the issues with inertial measurement sensors, and that inevitably when you integrate errors, and they have other properties like bias, constant biases and things like this, which to get a better estimate, you can estimate what those biases are and then remove them, things like this. Okay, have a state estimate. Once we're able to estimate where the position of the car is in space, then the next step we take is to actually control the vehicle. to make it go in a way that we want to go. So this is done in 2 stages. The first would be speed control independently, and then once we can control the speed, then we start looking at the steering. And so we can create a trajectory throughout the world using one of our path planning features in the Python APIs. And you can see here in the virtual as well as on the physical, the car driving around and through its city. They're not driving the same path, in case that wasn't obvious, but they are running the same code. The trajectory is completely up to you. We have a roadmap with the key points, so you can come up with your own trajectories as you like. But the point is designing the controllers and then being able to see how they perform, see how we can make them better, observing the things that happen like oscillation or instability. For speed control, it's based on a proportional integral control. And then for steering, we use the nonlinear Stanley controller. Once we have it driving around, we go into our final step, which is environment interpretation. And so with this, what we go through is how to construct a 2D map of the environment around a car. And so this, it depends on, we combine the state estimates of the car with the LiDAR scan data to be able to construct a 2D occupancy grid map of the environment. And so to do this, we have to drive around so you can see more things. On the scope there, you can see the top left image is showing you the raw LiDAR scan data coming in where the x-axis would be, I guess, the angle, and the y-axis is the range. Then we wrap it around to be in a polar form, and then we can integrate that over time to construct a map as we drive around. So there we go. So that's what we have so far. And the question then is, how do we actually use this? One of the main guiding philosophies here is to give you the flexibility and control to have the power to do what you think is best for you and your needs as an instructor. And because of that, we try to make it as open and modifiable as we like. We try to do our best to give you what we think you need and what we think is good for students, but you may have different opinions. And so you're free to take the lab guides and concept reviews that we created and use them as they are or modify them completely as you see fit. So we give you PDF as well as the raw docx files, so you can modify them as you like. As well, same thing with all the code. All of our code is in Python, and so it's completely open. You can modify it as you like. And the skills activities we've shown, they're good. They're good examples and good starting points, but it's by no means the end of what could possibly be achieved. And so if, for example, we look at the state estimation lab, we see the filters, the 3 filters we've chosen. If in your course you want to do something like a particle filter, that's fine. Just take it and modify it, and you can add it in as you like. So it's completely open in terms of what you want to do. And as well, so where can this actually fit, and how does any of this actually fit into a classroom? It can play a number of roles and over a number of different, well, as a student goes through their academic career, I suppose, and as they grow in competency, the level of detail and depth you can go into any one of these topics is going to vary. But it can start even in first or second year, doing things like being able to have a demonstration, using demonstrations to students, or using some of the, rather than having to implement more complicated technical aspects, giving them the solutions and guiding them on how to modify things to be able to get something out of that experience without having necessarily have to go into the detail. As well for lecture aids at any years. So this is another great aspect of the virtual labs. With the demonstrations as well, it's cool to show off in the physical thing, but that takes space and it takes time. But in any lecture, if you're running a PowerPoint, for example, you just pull up Quanser interactive labs, and you can in real time show whatever it is you're trying to teach and see how it actually performs on a car. So as a lecture aid, actually, Quanser Q Labs is very powerful and insightful tool. And as well, then they can go home afterwards and verify the results themselves. Um, in more of the upper years, the activities can perform as labs or longer durations or break them up into smaller chunks, but labs and in things like fourth year and as well grad school, then you start getting more into term long projects or research projects. So starting, for example, from the skills activities as a starting point, where can you go next? And what can you achieve over the course of a term? Um, how can you extend these results to do something more exciting? So that really leaves it very open-ended for the students to come up with. And as well, it's a great source for student competitions, SDCS in total. In fact, this upcoming American Controls Conference, we're having a competition where student teams from a few universities are competing to see to try and perform a different, I think it's environment mapping, complicated mapping and scenario for cities in unknown environments. But it's a competition that we're running, but between schools, but even within your school, um, it's always very motivating for students to compete against other students to see who can be the best in engineering in particular. Um, and in addition to not only time, also the space of the various courses in the university. Now, self-driving cars and self-driving vehicles is an obvious one, but really that's a field of many different subfields on its own. So each one of these tasks, SDCS serves as a great demonstration for applications of whatever content you're learning, be it state estimation or computer vision, as well as classical nonlinear control, multi-agent systems, machine learning, even something like concurrent programming, right? If you consider something like mapping an environment and being able to have a stable control, you need multiple independent threads running at different rates um, so that each one's guaranteed to perform within its allocated time slice, and how you manage this and share data back and forth between threads in a safe way. So areas you might not even expect, it can really bring some tangibility and real life applicability to more abstract content and computer science or controls and things like this. Um, so looking forward, based on the feedback we get from academia and the demand that we receive, our plan is to continue expanding on the set of skills activities that we've created so far and add more interesting research examples, similar to we've done with other products like the Cube, which I think is 40 labs at this point, uh, something like that. Um, some of the potential future talks that we've been thinking about doing include object detection and object avoidance, and then behavioral systems and decision making. So if you see an object in front of you, what do you do, right? Do you drive around it? Do you stop? Do you just plow right through it? How do you make these decisions autonomously? Um, and so these are some of the ideas, but really we're very open to receiving feedback. We love to get feedback because it makes us more relevant and with the demands of what people actually want to learn and things like this. Um, so in closing, SDCS gives you the tools and the power uh, to accelerate not just learning, but really to engage with students and perhaps most importantly of all, keep students engaged. Um, Ultimately, what you do with it's up to you. We put the power in your hands and give you the flexibility and the tools to create whatever experience you want to make, and hopefully the least painful way. Um, well, the least painful we can that we can do. Um, yeah, and that's all from me. So, any questions? Well, I guess John, you can take it away.
All right, thank you very much, Mitchell, for the amazing presentation. So I think we can proceed to the Q&A session. If you have any questions after the webinar, please visit quanser.com or email info@quanser.com. We'll be happy to chat with you. Last but not least, thank you again for joining us today. And so some of the questions that have come in during the webinar session. I can handle the first two, which is the support for ROS. So the Q car has ROS 1 and ROS 2 support. The ROS 1 distro is melodic, and the ROS 2 distro is dashing. These are tied to the operating system of the car itself. An interesting question for you, Mitch. Can you set up the driver's point of view during the simulation? In some of the videos you showed, there was a little bit of the virtual environment. So is this possible to do when you're driving around?
The driver's point of view, eh? So we can the virtual is a mirror of the physical, right? And we give you that and only that. So what you can see uh, during the demo that I showed, it goes to look around at the different cameras. So the Q card itself has 4 CSI cameras, providing like one in the front, one on the back, 2 on the sides. So you get a full 360 view. You can look at each of those cameras individually or together. As well, we have an Intel RealSense, which is an RGB depth camera pointed forward. And so you can see the image feeds coming from any of those cameras. As well, you can see the LiDAR scan. So if you want the specific perspective of a car, like somebody sitting in the car and driving around, no, we can't do that. At least not at this time. I mean, it's technically possible, but I guess if there's enough of a demand, we can do it. But at this time, really, it's just trying to give you what the car is and exactly that.
Right, thank you. Another question that has come in, so related to the teaching component, how much work is typically required for a student who wants to transfer their work over from the virtual to the physical car?
Yeah, that's a very good and important question. It's surprisingly actually not much. Uh, Actually, like when developing all the content, it was first done in the virtual world. Um, and that was done over quite a while. And then when it came time to actually test it, because well, iterating through the development and getting everything figured out, any bugs or anything like this, takes time. But it's much faster when you can do it very quickly, iterate over your code in the virtual. You don't have to worry about batteries dying or losing a connection or having to pick it up and put it back. So development was done internally, primarily in the virtual, and then we validated on the physical. And well, something that took I don't know, maybe a month to do in the virtual, it was working on the physical within a day, really within a few hours. So it actually works quite well, to the point that it's our primary development mode internally. Um, there are a few nuances, obviously, in switching from one to the other, which we discovered ourselves for starting, things like timing issues or other stuff like this. But given our own testing, we've been working to try and alleviate these nuances as well to make it as seamless as possible. So it works quite well, actually, um, which is something that we're pretty happy and proud about. Um,
Okay, thank you. Um, Looking at some more of the questions that have come in, how does one access the documents to see in more detail? So there are two complements for this question. There is the documentation for the virtual environment, which is already available online that you can go in, and this gives you more information about the different maps that Mitchell showed during the presentation. One we saw was when he was driving around with panels on the side, and the car was driving around, which we call our studio scenario. So how do you interact with the car? How do you set up? There are a series of examples for our Quanser virtual implementation. So that is already available. We're in the process of now documenting and getting ready what are the Python application libraries and the high level libraries. Those are still in the process. But with the upcoming release of the next set of labs, you will be able to see more documentation available on the virtual environment. Um, Another question that has come in, what is the application of virtual and real linkage in teaching? What is the difference between autonomous vehicle testing and the loop? And I think we kind of touched on this a little bit, looking at which is the idea of simulating the car as we saw in our virtual environment, um, and then transferring it over to the physical side. And then when it comes to teaching, as Mitchell described, these are topics that are related to autonomous vehicles and the individual components. And so the idea on the virtual side, as we mentioned, is hey, a student can figure out how to do control, how to do state estimation as fundamental tools for them to then expand on in their research. If maybe they like the idea of being able to figure out where the car is, then they can go down a specific research route in that sense. Um, Mitchell, another question for you. Do you offer any hands-on workshop with real hardware?
Uh, Me personally, I mean, I can, or we can as a company. Uh, we typically we perform training or other workshops as requested from any customers. So oftentimes when customers will order something like SDCS, they'll often hire us to come down to give them a few days of training for both their grad students and technicians and anyone else who's planning to use it. So we go through them. Ideally, it's set up by the time we get there, so we can do more interesting things. But as needed, get them up and running with the hardware and show them how to actually use it to do what them it needs. And also, typically, we'll consult with them to ask what it is they themselves are specifically interested in, and we can show them how to point them in the right direction for that. So that's a common thing that we do. And as well, we're always open to workshops and things. I think we typically, yeah, I don't know, John, if you can add to that, but that's, yeah, if it's something you are interested in, definitely reach out. And we do that kind of thing upon request.
Okay, perfect. Thank you. Yes, that's usually a training component where we will go in and then look at more of the actual cue car itself, and that's more tailored as a final experience that is in line with the prof and their interests, and also accompanied with the students. So that is definitely something we offer. Um, so, as I mentioned in the beginning, this webinar is being recorded. If we haven't had the chance to answer your questions, visit Quanser.com or info@quanser.com, and we'll be happy to chat with you. Last but not least, thank you again for joining us today, and have a great day or night ahead.